starting with the chapter called atomic structure. Okay, very simple chapter. You all probably know more than me because you are studying this chapter since time immemorial. Yeah, huge. All the concepts and all you must be knowing better. But just having a quick review, okay, a glance to the key words, the important points for this chapter. In atomic structure, first, I'm going to talk about an atom. We always used to say that atom is the smallest indivisible particle or unit of a matter, right? So atom, can I say, was indivisible, but that was a prior information. Currently, I can say the atom can be subdivided or can be divided into the subatomic particles. We call them as protons, neutrons and electrons. Protons are positively charged, neutrons are no charge, electrons are negatively charged. And obviously, protons plus neutrons, right, protons and neutrons, they make up a nucleus. So in our view, in our syllabus, talking about the general ideology, a nucleus consists of two things, protons and neutrons. Protons positive, neutrons no charge. So eventually, okay, on a whole, nucleus is positively charged. Surrounding the nucleus, we have electrons. Electrons, they revolve in orbits. So electrons revolve in orbits. Orbits are also called shells. They are also called energy levels. Right? They are also called energy levels. And electrons are not randomly distributed in the orbit. Nope. There is a specific formula for the placement, for the location of electrons in the orbit. Right? So basically, protons plus neutrons together make up a nucleus and they are called nucleons. What are they called? Nucleons. That's a name given to them. Right, with this, fine. So this is what an atom basically at our level consists of. Alright, now I'm going to talk about certain terms like a mass number and atomic number. So my second terminology is atomic number. Okay, atomic number is represented by the symbol Z. When I write an element, for example, I write an element X, the atomic number is generally written at the bottom. This is the positioning of an atomic number. So whenever, an example, whenever I'm talking about an atom called sodium, Na is sodium, and I write 11 at the base, can I say sodium is an atom, an element having 11 as the atomic number? Fine with this part. Second, atomic number is nothing but the number of protons, or it is the number of electrons in an atom. So can I say sodium has 11 protons, it has 11 electrons, because an atom is electrically neutral. An atom is electrically neutral, right? Because if it has the same number of protons and electrons, it's neutral. Fine. Atomic number, 2 points. One of them is the symbol, number of protons, generally written on the base. Talking about the next concept, the third concept is about the atomic mass number. Yeah. Atomic mass number is represented by A as a symbol, and usually it is represented at the top. A. Atomic number is the number of protons plus neutrons, or you can say electrons plus neutrons. Simple language. Because this number of protons and number of electrons in an atom will be the same. So if there are 11 protons, obviously there are 11 electrons. So the variation, the difference is going to be in neutrons. So if I continue with the same example, we have sodium 2311. So can I say sodium has 11 protons and 23 protons plus neutrons. Now, listen. Out of 23, 11 are protons. Out of 23, 11 are protons. Can I say 11 plus neutrons is equal to 23 as a totality? So that means the number of neutrons are 12 in my example. Because obviously 11 plus 12 makes it 23. That's how I get the number of protons, neutrons and electrons in an atom. Right? Alright. So after my atomic mass number, the next concept is about the isotopes. Alright. Isotopes are structures of elements having same atomic number, different atomic mass number. Didn't understand? Hold on, man. Simple language. Same atomic number, same bottom, same Z, but different atomic mass number, different A. Let's take an example to analyze and understand it. Example, many of them. One of them is oxygen, 816, 817, 818. That means these are the three elements of oxygen which are present in the air, the atmosphere on Earth. Okay, so in all of them, the atomic number of oxygen is the same. Now what's that? Can I say the number of electrons, the number of protons in an oxygen for all three of them is the same. So where do they differ? They differ in the number of mass number, that is the number of neutrons. The first oxygen has 8 protons, 8 neutrons, 16 minus 8. Second oxygen has 8 protons, 9 neutrons, 17 minus 8. And the last one, the third oxygen element, which I've written out there, the isotope, has 8 protons, 10 neutrons. That's 18 minus 8. Another example I can give you is hydrogen. H11, H12, H13. The first hydrogen which I've written is called a protium. The second one is called a deuterium. And the third one is tritium. These are the names of 3 isotopes. 1 proton in each of them and 1 electron in each of them. This has 0 neutrons. When you subtract 1 neutron, subtract 2 neutrons. So what is the speciality of an isotope? Can I say in an isotope, the electronic configuration remains the same. Now what's that? Wait, hold on. Electronic configuration is the same. Now I'm just going back. I'm just drifting away from my topic for a moment. Electronic configuration. What's electronic configuration? It is the arrangement of electrons in the orbit of an atom. I didn't get it. It's too difficult to digest. Well, one moment. It is the arrangement of electrons in a shell or in an orbit in a particular manner, not just a random way. Okay, and that way we'll study after like 5-10 minutes. Okay, so can I say in this, all the examples which I have taken of hydrogen, can I say it has 1 electron? That means the electronic configuration, the number of electrons remain the same. And remember, it is the electronic configuration which governs, which has a control for the chemical properties. Now that hits hard. Can I say electronic configuration is the one who is responsible for the chemical behavior of an element. Now tell me one thing, in all these 3 idiots, can I say the number of protons or the number of electrons is the same? That means the electronic configuration is the same. That means they show similar chemical properties. That's awesome. So can I say isotopes, the chemical properties are, don't write same, they are similar. If you write the word same, they won't give you marks in the exam, sorry. They're similar. But their physical properties are different. Yeah, their physical properties are different, guys. Now, what are you talking about the physical properties? Physical properties, the weight, the density, the mass, the color, the shape, the size, these are called physical properties. So when you observe them, they are going to differ, okay, in the nature, in their look, the appearance, the behavior, but the chemical properties remain the same. So this is one of the speciality of an isotope. All right, so we spoke about four characteristics, four things, four key points. We spoke about an atom, the atomic number, the mass number, the isotopes, the electronic configuration. Right with this? Okay. Now there is something called as isobars. Alright. Isobars is not in syllabus. I won't enter into much of depth, but a small overview by giving an example of what an isobar is. Right? I can take an example of calcium and argon. 40 as the weight for both of them, 20 and 18. From here, can I make it out that calcium and argon, the mass is the same. There is a difference in their atomic numbers. So can I say there are 20 protons and there are 18 protons. So there are 18 electrons and there are 20 electrons. Don't these two elements have difference in the number of electrons? And if there is difference in the number of electrons, obviously their electronic configuration will differ. Thus, their chemical properties will differ. They might be same in the similar in the physical properties. I'm not, keen on that. But their chemical behavior. Now, some students ask me, sir, what is chemical behavior? It is the way they react in a chemical reaction. So obviously, reaction of calcium with an acid and reaction of argon with an acid is going to be different because chemically they show variety in properties. So these are isobars. Isobars are elements having same mass but different atomic number. So this was the first portion of our chapter. Quickly go through it and we'll bang on with the next one. Talking about the placement of the electrons in the shell, the orbit, right? It is not random, I said that. The sixth one you can take, the fifth was isobars. And now when you're talking about the nucleus having neutron and proton, then we have shells. This is the first shell, second, third and so on. The shell which is closest to the nucleus is called the K shell. L, M, N and so on. So these are the names given to the shell. So can I say K shell is the closest to the nucleus. So our nucleus, okay, gives a lot of power, a lot of energy to the K shell. So I can say the innermost shell, this is the innermost orbit, the K orbit has maximum energy. And if an electron is placed in the K shell, it has a capacity. The innermost shell can hold maximum up till only 2 electrons. So one out here, one out here. And these electrons, they have minimum energy. So the shell which is closest to the nucleus has maximum energy and the electrons in that shell have minimum energy. And I can say the first shell has a capacity, the holding capacity of 2 electrons. Second shell has a capacity of holding maximum up to 8 electrons. Third shell, 18. Fourth shell, 32. Now this is represented by a general formula. The formula is 2n square. This formula determines the upper limit, the holding capacity of a shell. For instance, if I substitute n as 1, 2 into 1 square, which is 2. Put n as 2. 2 square is 4. 4 twos are 8. So the second shell has a capacity of 8 and so on. So this formula is very important. It helps me. It makes me understand the maximum number of electrons a shell can handle. Alright. Now, based on this concept, we have a rule which is called octet rule and a duplet rule. So my next answer for y'all is octet, duplet. Okay, du means 2, octagon means 8. So can I say the shell, right? If I'm talking about a shell made up of helium, a shell of helium. Example, helium is an element having 2 electrons in the only shell and the outermost shell. After helium comes lithium and the electronic configuration is 2, 1. Can I say out here, you can't have 3 electrons in the outermost shell or the only shell, right? Lithium cannot be written as 3 because after helium, one more shell, one more orbit increases, because maximum which a first shell, the innermost shell can take is 2. Fine. I will say helium is the only duplet which we have with us. Duplet because it is stable. Everyone on this earth, guys, you, me, everyone on this earth want to become stable. We want to have a steady life. We want stability in our lives, right? Everyone wants it. No one wants a tinge of, up and downs in the life. We want easiness in life. So every element on this earth wants to become stable. So God put a condition. What is the condition of stability? It is to form either an octet or a duplet. That means a lithium, what will a lithium try to do? A lithium will say, I want to give away my 1 electron. If I give away my 1 electron, I will have 2 in the only shell. Lithium will not become helium. That's the misconception. Lithium will get a configuration like helium, but it will not be transformed into a new element altogether. You understand what I'm saying, right? So can I say this is called a duplet behavior, the duplet, to attain duplet nature. So I can say lithium wants to become a duplet, wants to become stable. Similarly, if I take an example of chlorine, the electronic configuration is 287. What will chlorine try to do? It will try to gain 1 electron and attain the configuration of 288. Isn't there 8 electrons in the outermost shell? And if there are 8 electrons, can I say we call it as an octet behavior? So octet means 8 in the outermost shell, duplet means 2 in the outermost shell. Are you understanding, guys? So every element on this earth wants to be stable, for which it tries to attain octet or a duplet stability, right? One more thing. If I take an example of calcium, the electronic configuration of calcium is 2882, right? Now, listen. The third shell, this bloody third shell, doesn't it have a capacity of 18 electrons? 18? Now, listen to this explanation. This is my third shell. I know that the third shell can capture 18. Then why did I write 8, 2? I should have straight away written 2, 8, 10. Because obviously, if the holding capacity is 18, it can easily hold 10 electrons. Very simple. But there is one more rule. That if it is the last shell, so I can say that 10 electrons, though it's in the capacity, in the limits, it won't take it because it's the last shell. And there is another rule, as I said, that if it is the last shell, then come what may be the capacity of the shell to hold an electron, whatever the capacity is, I give a damn. No, it will only hold 8 electrons. So capacity of this shell can be anything. It can be 32, 64. But if it is the last shell in that orbit, no matter whatever the capacity is, irrespective of the holding capacity, the holding limit, it will have only 8 electrons in the outermost shell. So there you can't have a 10. The 10 has to be broken down into 8 and 2. So this is the reason that if it's the last shell, then irrespective of the holding capacity, it will only take 8 electrons. Remember that. Now that's called an octet rule and a duplet rule for you. And everyone wants to become stable, as I said. Okay, after this, going on with the actual atomic structures. Okay, I'm going to take few elements. They are very easy to be made. First, we'll talk about atomic structures of elements, followed by compounds. Yep. And in compounds, we are going to talk about two types of bondings. Ionic bond, which is electrovalent bond, and a covalent bond. 3 examples I'll be taking for atomic structure of various elements for drawing purpose. Which ones you all want? Tell me now, come on. We'll take aluminium. Second, we'll be taking, take your wish here. Let's take sulfur, something different. Sulfur is a non-metal, aluminium is a metal. And let's take oxygen. Yep. Oxygen I'm going to take in water, so I'll take some other element, some simple one. Let's take boron. Fine. A simple one. So talking about the electronic configuration to start with. Aluminium is going to be 283, sulfur 286, and boron, okay, boron is 2,3, I guess, yeah. 2 shells, 3 shells, 3 shells. Okay. First, we have nucleus. Nucleus has neutron and proton. If you count, add on, there are 13 electrons. Add 16 electrons, 5 electrons. Okay. So the distribution is like 2 plus 8 plus 3. So we have neutrons, protons, first shell, second shell, and the third shell. Similarly, nucleus, first shell, second shell, and the third shell. First shell, second shell, neutron, protons. Okay, now placement. Most of the schools now, they have a particular order of placement. What they say is, first shell has 2 electrons, that's okay. Then second has 8. You make in a group of 2. That means 2 out here, 2 out here, 2 out here, and 2 out here. That's how it makes it 8. But that is okay. It belongs. There is no specific rule as of now, right? It matters from school to school. So you please follow what your school teacher has said with respect to the location of these electrons. Okay, and we have 3 electrons in the last shell. So you can put it as 1, 2, and 3. Okay, talking about sulfur. Sulfur, 2 electrons in the innermost shell. Then we have 8 electrons. You can also have a placement like this. 1, 2, 3, 4, 5, 6, 7, and 8. And 6 electrons in the last shell. 1, 2, 3, 4, 5, and 6. And out here we have 2 electrons and we have 3 electrons. That's it. Very simple. Ideally, most of the students also learn the mass number. What I've written out here, this is the atomic number, which is the number of protons or electrons. You should know the mass also at this level. Yes, the mass number of aluminium is 27. That means it has 14 neutrons and 13 protons. Sulfur, the mass number is 32. Ideally, the mass number is almost, for the light elements, the mass number is almost double of the atomic number. 13's double is approx 26. The double of 16 is approx 32. Yep, approximately it is double. So that tells me, okay, that gives me an information about the number of neutrons also. After this, going on with compounds having ionic structure and covalent bonding. First, let's differentiate between ionic bond and covalent bond. Okay, the first point. Ionic bond is a bond which is also called electrovalent bond. Okay, and covalent is a sharing bond. Ionic bond is formed between a metal and a non-metal. So it is a bond which forms, okay, which is formed between a metal when a metal reacts with a non-metal. Covalent bond is usually formed between two non-metals. Okay, the second pointer. Ionic bond is a strong bond in which a metal is held, okay, the metal is held with a non-metal. Both of them are attracted to each other by a strong electrostatic force of attraction. So it's a strong bond, and this bond is formed between both of them by a strong electrostatic force of attraction. Okay, talking about a covalent bond, it is a weak bond. It's a weak bond, sorry. In which the atoms are held together by weak van der Waals force of attraction. Remember this. Talking more about ionic and covalent bond, the other name you can put it as a differentiation, but remember, the other name is also called electrovalent bond. Okay, and the fourth point, the last point, I'm not writing it down, but just remember, ionic bond is formed by a give and take relationship between a metal and a non-metal. There is a transfer of electrons. A metal gives, a non-metal takes, right? Covalent bond is formed by sharing of electrons. They both contribute equally, okay, in the sharing. So this is a give and take relationship. Okay, this is like you also share, I also share, we both share, like a mutual understanding, right, with this. So this was the differentiation, and we're going to draw, okay, we are going to draw two things. We'll draw atomic structure, and we are going to draw an electron dot or a cross structure for bonds having ionic bonding and bonds having and compounds having covalent bonding. Some of the examples of ionic bonding are NaCl and calcium oxide in our syllabus, and for covalent bonding the examples are water, sharing of electrons. You can talk about chlorine, etc. So we're going to draw four structures and understand what an atomic structure between the compound looks like, right? So go through this and we'll proceed with the last part of the chapter. Talking about the ionic bonding, the ionic structures, right? We're going to talk about the electron dot and a cross structure and the atomic structure also. So starting with the first example of NaCl, sodium chloride, right? It is obviously sodium is a metal, chlorine is a non-metal. So a bonding between a metal and a non-metal is an ionic bond. Fine. Sodium, you talk about the configuration. That's how you'll start with. 281. It will give away one electron. And chlorine, 287. It will accept one electron. So it's a transfer of electrons, a give and take relation. Starting with the electron dot structure. Okay, in sodium, you have only one electron in the outermost shell. reacts with chlorine having 7 electrons in the outermost shell. So this electron will be transferred from sodium to chlorine, alright, and you will have Na. Na becomes 1 plus because it has lost electron, it becomes electropositive, and chlorine, it gains that electron and it becomes 1 minus. So the bond formed together is called a sodium chloride rock salt NaCl ionic bond electrovalent bond. Alright, if we talk about the atomic structure, sodium, you first have neutron proton, 2 electrons, 8 electrons and 1 electron. In most of the school, they ask you to only draw the outermost shell, right? So you can follow the structure of the school. I have no issues, respect the school. So we have 2 electrons in the outermost, in the first shell, then 8 electrons in the second shell, right? And 1 electron in the outermost shell. So we have 3, 3 and 2, 8. This reacts with chlorine. Okay, chlorine again 2, this is a nucleus, 2, 8 and 7 in this, the outermost shell. This is the most boring part. Alright, and then you can show the transfer of electron from the valence shell of sodium to the valence shell of chlorine. So I can say this is going to be 2, 8, 1 for the moment. This is going to be 2, 8, 7. And when they combine together, right, they combine together, they form this. Alright, they form this. So we have NP 2, 8. And this is going to be NP 2, 8, 8, and this is simply going to be 2, 8. So basically this is going to be Cl minus, this is going to be Na plus, together forming a bond called NaCl. Okay, so you may just draw the electrons, it's just fine, it's basic. So you have 2 and 1, 2, 3, 4, 5, 6, 7, 8. I'm not drawing the circle, it's bugging. 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. It seems like I'm doing some zombie or some Zumba dancing or something like, right? So this is going to be the NaCl, the electron dot structure, and this is the atomic structure. My next diagram for you all as an electrovalent bond is calcium oxide. I call it as CaO. Yeah. Calcium, the config is 2882 and oxygen is 2,6. Can I say this is going to donate 2 electrons, this is going to accept 2 electrons? It's again a give and take relationship. Yep. So out here, so let's begin with the electron dot structure. Alright, we have calcium 2 electrons plus oxygen 1, 2, 3, 4, 5, 6 outermost shell. They get transferred forming Ca 2 plus and oxide 1, 2, 3, 4, 5, 6, 7, 8 2 minus forming calcium oxide. Okay, I am not drawing the atomic structure, it is very simple. Okay, if I draw, I am just drawing the outermost shell. Is that okay? Yeah. So in the outermost shell, you have Np and the outermost shell of calcium has 2 electrons plus Np, the outermost shell of oxygen has 6 electrons. Okay, there is going to be a transfer of these 2 electrons. So this is calcium 2882. This is oxygen 2,6. Together forming a bond Np. Now this is going to be empty, the last shell empty. So basically now it has only 3 shells, 288. It has attained a configuration very much similar to argon. Plus this is going to be Ca2 plus, and not plus exactly, but you can put a bracket here and a bracket here. So here is going to be oxygen. In the outermost shell, there are going to be 8 electrons now, stable. This is oxide 2 minus, forming together calcium oxide. So this was about the ionic bonding. Okay, talking about covalent bonding. In covalent bond, we have the first element called chlorine. This is ionic for you all, both 2 examples of ionic. Okay, talking about chlorine, Cl2. Chlorine, the electronic configuration is 287. Yeah, 287. Let's draw the cross structure or the dot structure. Chlorine, 7 electrons, 1, 2, 3, 4, 5, 6, 7. Another chlorine, 1, 2, 3, 4, 5, 6, 7. A single bond is formed between them. A dash, a bond represents 2 electrons. So in a sharing of electrons, there is a contribution of 1 electron by each of the atom. So this forms Cl dash Cl, which forms Cl2. And if I draw a direct combination structure, the atomic structure, it's going to be Np. I'm drawing only the outermost shell. Yeah, that's the outermost shell, Np. So it's going to be sharing of electrons, right? Yeah, now we have 1, 2, 3, 4, 5, 6 and 1. These are the 7 electrons of this chlorine atom. And talking about the other one, 1, 2, 3, 4, 5, 6 and 7. That means, guys, now tell me one thing. If you talk about this atom, hasn't it now obtained 8 electrons, where one of them is a shared portion of the other chlorine atom. So each of the atoms have got 8 electrons and they both have attained stability. So chlorine, we call it as a diatomic molecule. Okay, talking about water. Okay, so this is Cl2. Alright, water. Water is H2O, in which hydrogen, the configuration is 1, oxygen, the configuration is 2, 6. Talking about the first, the dot and a cross structure. 2 hydrogen, 1 oxygen. So we have hydrogen, oxygen, 6 electrons and another hydrogen. A bond out here, a single bond out here. It makes H-O-H. Oh, and that is nothing but water, H2O. Okay guys, HOH, that's the structure, man. That's water for you all. This is the dot and a cross structure. If I talk about the atomic structure, right, I'll directly draw the combination structure. H, just the outermost shell. Then we have O and we have H again. So we have a proton. In hydrogen, we have a proton. Usually, hydrogen has isotopes. If I'm talking about tritium or deuterium or protium, these are the 3 isotopes. Here I have taken an example of a protium. Protium has only 1 proton, no neutron. So there is just 1 proton and 1 electron. So these are 1 electrons which are contributed in the sharing by hydrogen. Oxygen, yep. Neutron, proton, it has 6 electrons. 1, 2, 3, 4, 1 in the sharing 5, another sharing 6. Now tell me one thing. Hasn't hydrogen become a duplet? 2 electrons. Hydrogen become a duplet, 2 electrons, and the oxygen octet with 6 electrons, all are stable. That's the atomic structure, the combined structure for you all. So this leads me to the end of my chapter of atomic structure. A lot of diagrams for drawing purpose are going to come more than the theoretical part, right? So go through this chapter and it has been successful for you all. Thank you.